In a previous module, we had learned the different assumptions that we need to make while fitting a linear model to a dataset. One of the assumptions was that successive error terms were not correlated to each other. But sometimes this assumption is violated. In case where we have successive error terms related to each other, we say that autocorrelation is present. In the presence of autocorrelation, the inferential procedure on the regression parameters are faulty. And because of that, we need to find ways of removing autocorrelation before fitting a linear model to the data. But in order to find remedies for autocorrelation, we first need to make sure that there is indeed autocorrelation present in the data. In this module, we will learn 3 different tests that will help us detect autocorrelation, and then in a separate module, we will discuss the remedial measures that we take for autocorrelation. In a previous module with the title Autocorrelation in Regression Part 1, we had learned the definition of autocorrelation in a regression setup, and we had also looked at the serious consequences of the presence of autocorrelation. Now we need to find remedies for autocorrelation before fitting a linear model to the dataset. But before we use remedial measures, we need to make sure that autocorrelation is indeed present in the dataset. And to that end, we have to look at several tests which help us detect autocorrelation. In this module, we will discuss 3 such tests, but the first method, the most common method of detecting autocorrelation, is the graphical method, which we will discuss here. So in the graphical method of detection of autocorrelation, we use the residual plot to detect autocorrelation. We draw a graph of the estimated residuals epsilon I hat against time. If there is a cyclical pattern in the plot of the points, or if there is any kind of pattern over time of the plot, then we can conclude that there is autocorrelation present. If successive residuals tend to cluster on one side of the zero line of the other, it is also graphical indication of the presence of autocorrelation. Now, we have to note here that as the first step towards identifying the presence of autocorrelation, it is a good practice to plot epsilon I hats against time and look at the clustering effect of the plots. Although this method is a very crude method of detecting autocorrelation, but considering this as step 1 is very helpful. Now let us look at more complicated method of detecting autocorrelation, or rather more mathematical tests to detect autocorrelation in a data set. The first test that we will discuss here is the run test. A run is defined to be a succession of one or more identical symbols which are followed and preceded by a different or no symbol at all. For example, here we can see a sequence of plus and minus. So each of these are called run. First we have 2 plus sign, which is the first run, and the second is of 3 minus signs. So this is another run. So in the run test, to test for autocorrelation, the hypotheses that we wish to test are H naught, which is the null hypothesis. It says there are no autocorrelation problem in the model, and HA, which is the alternative hypothesis, says that there is autocorrelation present in the model, and we wish to test the null hypothesis against the alternative hypothesis. Now, if I talk about the residuals in case of a linear model, we can actually see that if the residuals that we obtain after fitting a linear model are positive and negative, and if we write down the symbols of these positive and negative residuals, then we can actually create a run which is very similar to the one defined above. So if we have a cyclical pattern of plus and minus, then we can say that there is a pattern in the plot or in the sign of the residuals, and thus use the run of plus and minus residuals to detect autocorrelation. So for the run test to detect autocorrelation, let us define the following terms. Let's say N1 gives us the number of positive symboled residuals, N2 is the number of negative symbol residuals. N, which is the sum of N1 plus N2, which is nothing but the total number of observations or the total number of residuals. And R is the number of runs. Under the null hypothesis that successive outcomes are independent and assuming that both N1 and N2 are positive numbers, the number of run is distributed normally. That is, the number of run R is distributed with mean 2 times N1 N2 divided by N1 plus N2 plus 1 and with variance 2 times N1 N2 times 2 N1 N2 minus N2 divided by N1 plus N2 times N1 plus N2 minus 1. So, the distribution of a run is normal with the mean and the variance as I have defined here. Now, the run test tells us that if the number of observation is greater than 25, or in other words, if the sample is large enough, then the appropriate test statistic for this test is given by Z, which equals R minus expectation R divided by standard deviation R or square root of variance R, which is normally distributed with mean 0 and variance 1. In other words, the test statistic is a standard normal test statistic. If the hypothesis of randomness is sustainable, we should expect R, which is the number of runs obtained, to lie between expectation R plus minus 1.96 times sigma square R, where sigma square R is the variance of number of runs with 95% confidence. In other words, the interval that I have just defined is the confidence interval with confidence level 95%. Now, when we perform the run test, the decision rule is such that we do not reject H naught or null hypothesis if the number of runs R falls between expectation R minus 1.96 times sigma R and R is greater than expectation R plus 1.96 times sigma R, and we accept it otherwise. The next test that we use to detect autocorrelation is the Durbin-Watson test. Now, let us look at the multiple regression model with autoregressive of order 1 error, and it is given by yt equals beta naught plus beta 1 xt1 plus beta 2 xt2 plus beta k xtk plus epsilon t, where yt is the response and xt1, xt2, xtk are the response variables, are the predictor variables. Epsilon t is our error term, and since there is autocorrelation of order 1, epsilon t can be written as epsilon t equals rho times epsilon t minus 1 plus ut, where rho lies between minus 1 and plus 1. The Durbin-Watson is the most celebrated test detecting autocorrelation, and it was developed by J. Durbin and G. S. Watson. Using the Durbin-Watson test, we test the hypothesis that null hypothesis says rho equals 0, in other words, the errors are not correlated, and the alternative hypothesis says that rho not equals 0, that is, the errors are correlated. As you can see, under the null hypothesis, rho equals 0, if we plug rho equals 0 in the autocorrelation 1 equation above, we have epsilon t equals ut, or in other words, there is no correlation between epsilon t and epsilon t minus 1. So, here is the Durbin-Watson test statistic. By the definition, the Durbin-Watson test statistic D is given by summation t equals 2 to n epsilon hat t minus epsilon hat t minus 1 whole square divided by summation t equals 1 to n epsilon t hat square. And we can through a few algebraic steps, we can actually reduce D, which is the Durbin-Watson test statistic, and write in terms of rho, which is the correlation coefficient between epsilon hat t and epsilon hat t minus 1. So, as we can see here, we can write D equals 2 times summation epsilon hat t square minus 2 times summation epsilon hat t minus 1 divided by the denominator is same as before, which is summation t equals 1 to n epsilon hat t square, or we can also write 2 times 1 minus summation epsilon hat t times epsilon hat t minus 1 divided by square root of summation epsilon hat t square and summation epsilon hat t minus 1 square, where summation epsilon hat t square and summation epsilon t minus 1 hat square differ only by one observation, and so they can be approximated to be equal to each other. Thus, the final result gives us the form of Durbin-Watson test statistic as d equals 2 times 1 minus rho. Now, before we move on, let us look at the range of the Durbin-Watson test statistic. We know that the range of rho, which is the correlation coefficient, is between -1 and 1. Since Durbin-Watson d statistic is a function of rho, the range of this test statistic is also dependent on the range of rho. So, when rho equals 0, d equals 2, when rho equals 1, then d equals 0, and when rho equals -1, d equals 4. Thus, the extremes of the range of d statistic is given by 0 and 4, or in other words, 0 less than equals d less than equals 4. Now, let me walk you through the mechanism of Durbin-Watson test. There are several steps involved in this process. Let us look at them in detail. So, to estimate the model by OLS, we first compute the residuals epsilon t. The first step involved in the Durbin-Watson test is to estimate the model by OLS, or the ordinary least square method, and obtain the estimates of the parameters. We then plug these estimates of the parameters in the regression model and we compute the residuals. In other words, we compute the residuals from the fitted model as yt minus beta naught hat minus beta 1 hat xt1 minus beta k hat times xtk. We then compute the Durbin-Watson test statistic using the residuals that we have computed using the fitted model, and d is given by summation t equals 2 to capital T epsilon t minus 1 square divided by summation t equals 1 to capital T epsilon t square. Now, we have seen that the range of the Durbin-Watson statistic d is between 0 and 4. The exact distribution of the test statistic d depends on rho as well as the observations on our predictor variable x's. So, Durbin and Watson had showed that the distribution of d is bounded by two limiting distributions that give the critical values for the limiting distribution of d, and they are denoted by dl and du. So, if the reader is interested, you can look it up that there is a table which gives us the values of dl and du for different levels of significance and for different sample sizes. Now, the next step in Durbin-Watson test is to test the null hypothesis H naught, that rho equals 0 against H A, rho greater than 0. We at first have to find a critical value for the Durbin-Watson statistic, which is dl and du. We can do that using the standard Durbin-Watson critical value table. We reject H naught if d is less than equals du, and we do not reject if d is greater than equals du. Thus, if d is in between dl and du, the test is inconclusive. To test for negative autocorrelation, that is, now our alternative hypothesis is that HA such that rho is less than 0, we use 4 minus d as the test statistic in place of d. This is done when d is greater than 2. If 4 minus d is less than dl, we conclude that there is significant negative autocorrelation. If 4 minus d is greater than du, we conclude that there is no negative autocorrelation. The test is inconclusive if 4 minus d lies in between dl and du. Here are a few important remarks about Durbin-Watson test. The inconclusiveness of Durbin-Watson test arise from the fact that there is no exact small sample distribution for the Durbin-Watson statistic D. If the reader can recall, when I started discussing Durbin-Watson test statistic, the assumption was made that let us assume the sample size n is greater than 25. So, any sample size which is less than 25 or any sample which is very small in size, Durbin-Watson test statistic does not perform very well for such samples. From estimated residuals, we can obtain an estimate of the first order autocorrelation coefficient. We can obtain an estimate of the autocorrelation coefficient rho given by the expression rho hat equals summation t equals 2 to capital T epsilon t times epsilon t minus 1 divided by summation t equals 1 to capital T epsilon t square. This estimate is approximately equal to the one that we obtained by regressing epsilon t against ut minus 1 hat without the intercept term. It has been shown that D is approximately equal to 2 times 1 minus rho hat. The third remark about the Durbin-Watson test is that, as we have seen earlier, the range of rho is between minus 1 and plus 1, and as a conclusion we had seen that the range of D was obtained as 0 and 4. When rho takes a middle value 0, which is the middlemost value of rho, then D takes the value 2. Thus, the Durbin-Watson statistic approximately equals 2 means that there is no first order autocorrelation between the error terms. A strong positive autocorrelation means that rho is close to plus 1 because rho represents the autocorrelation coefficient. Similarly, values of D close to 4 indicate a strong negative correlation because when rho equals 1, D equals 4. Now, let us look at the third test that helps us detect autocorrelation in a data set. The Lagrangian multiplier test is used, and it is very useful in identifying autocorrelation not only for the first order but of higher orders as well. And this is one of the reasons that has made the Lagrangian multiplier test a very popular test among statisticians, because in many cases the autocorrelation is not of order 1 but more than 1. In such cases, we can use Lagrangian multiplier test unlike the Durbin-Watson and the run test to detect autocorrelation. Now, let us consider the following multiple regression model, where we have response variable yt equals beta naught plus beta 1 xt1 plus beta 2 xt2 plus beta k xtk plus rho times epsilon t minus 1 plus ut. As you will notice, we have here replaced epsilon t by rho times epsilon t minus 1 plus ut, and this is because we are assuming first order autocorrelation between epsilon t and epsilon t minus 1. The test for the autocorrelation coefficient rho equals 0 can be treated as the LM test for the addition of the variable epsilon t minus 1 to the model. Now, here are the steps involved in Lagrangian multiplier test. Here again we first estimate the regression model by OLS, just as we had done in case of Durbin-Watson test, and after fitting the regression model we compute the estimated residuals, which are given by epsilon hat t. Now, we regress epsilon hat t against a constant set of predictor variables xt1, xt2, xtk and epsilon t minus 1 using t minus 1 observations from 2 through t. Then the LM statistic can be calculated by capital T minus 1 times r square epsilon, where r square subscript epsilon is the r square from the auxiliary regression that we obtain by fitting epsilon t hat against xt1, xt2, xtk and epsilon t minus 1. Now, we reject the null hypothesis H naught that rho equals 0 of 0 autocorrelation in favor of the alternative that rho not equals 0 if our test statistic is greater than the critical value chi-square 1 minus alpha, where the value of chi-square 1 in the chi-square distribution with 1 degrees of freedom such that the area to the right of it is 1 minus alpha, at alpha is the significance level. Here are a few remarks about the Lagrangian multiplier. If there was autocorrelation in the residuals, we would expect epsilon t to be related to epsilon t minus 1. This is the motivation behind us fitting an auxiliary regression in which epsilon t minus 1 is included along with the independent variables in the model. A second remark is that unlike the Durbin-Watson test, the Lagrangian multiplier test does not have inconclusiveness. However, one major drawback of the Lagrangian multiplier test is that it is a large sample test. Here again, just like Durbin-Watson test, we need a sample size of at least 25 or 30 for the test to be meaningful. Now let us look at the R code that we use to actually perform these tests on a data set using R. Here I have attached the data Hartnagel from the library CAR. Here is the data set, and using the function Durbin-Watson test on the object of LM function fitted to the data set will give us the autocorrelation Durbin-Watson statistic value and the corresponding p-value. As we can see here, the alternative hypothesis that we tested was rho not equals 0. So, for higher order correlation, in case we have higher order autocorrelation, in general the pth order autocorregressive process will be written as yt equals beta naught plus beta 1 xt1 plus beta 2 xt2 plus beta k xtk plus epsilon t, which is the multiple regression model, and epsilon t is now regressed on rho 1 epsilon t minus 1, rho 2 epsilon t minus 2 to rho p epsilon t minus p plus ut, and we have regressed epsilon t on epsilon t minus 1 all the way up to epsilon t minus p because we consider autocorrelation or autoregressive process of order p. So, the higher order autocorrelation can also be detected using Lagrangian multiplier. The Lagrangian multiplier test for higher order autocorrelation is obtained by combining the above two equations into one equation, which can be written as yt equals beta naught plus beta 1 xt1 plus beta k xtk plus, and now we replace epsilon t with rho 1 epsilon t minus 1 plus rho 2 epsilon t minus 2, rho p epsilon t minus p plus ut. And the null hypothesis we now wish to test is that all the rows are 0. That is, rho 1 equals rho 2 equals rho p equals 0 against the alternative that at least one of the rows is not 0. So, the steps involved in Lagrangian multiplier to detect higher order autocorrelation is somewhat the same as before, with only slight changes made to the test statistic and the degrees of freedom of the distribution of the test statistic. Here again we estimate the regression model by OLS and obtain its estimated residuals, and we regress the residual epsilon t hat against all independent variables plus epsilon t minus 1, epsilon t minus 2, epsilon t minus p. The effective number of observations here is t minus p, because t minus p defines only for the period p plus 1 to t. And then we compute the test statistic t minus p times r square subscript epsilon from the auxiliary regression that we have run in step 2. If this test statistic exceeds chi-square p times 1 minus alpha, the value of the chi-square distribution with p degrees of freedom such that the area to the right is 1 minus alpha, we then reject the null hypothesis that rho 1 equals rho 2 equals rho p equals 0 in favor of H1. Autocorrelation, as we have seen, is one of the very important assumptions of linear model. In this module, we have learned 3 different tests, namely the run test, the Durbin-Watson test, and the Lagrangian multiplier test for detecting first order autocorrelation, and I have also discussed the use of Lagrangian multiplier test in order to detect autocorrelation of the order k. There are several methods that we can use to find remedies for autocorrelation, and we will dedicate a separate module to the study of remedial measures for autocorrelation in linear models.